Hi, my name is Satish Pichavan. Today I am here to give a seminar on ECOS and a tiny operating system. Here, ECOS stands for Embedded Configurable Operating Systems. ECOS is an open source or a royalty free. It is a real-time operating system. It is most widely used embedded operating system targeted at high performance and a small embedded systems. An embedded form of Linux or other commercial operating system would not provide the streamlined software requirements. This is the ECOS configuration tool. ECOS configuration tool, which runs on Windows or a Linux, is used to configure an ECOS packages to run on target embedded system. The complete ECOS package is structured hierarchically, making it easy. At top level, ECOS consists of number of components and the configuration user may select only those components needed for the target applications. For example, a system might have a particular serial I/O devices. The configuration user would select a serial I/O for this configuration. The configuration tool would include minimum necessary software for a support. The configuration user can also select specific parameters such as default data rate and size of an I/O buffer to be used. Here it is a top level of an ECOS on the configurable tools as seen by the users. Each item present in a left hand side can select or a deselect when it is highlighted. This is the lowest right hand side of the window provides a descriptions and a right hand side window provides a link to a further document plus additional information about the highlighted items. This is an ECOS configurations tool in an kernel. The ECOS kernel options in this figure. Note that exception handling has been selected for inclusions but SNP has been omitted. This is an overall process of creating a binary image to execute in an embedded system. This process is run on a source system such as Windows or a Linux platform, and the executable images is designed to execute on a target embedded system such as a sensor in an industrial environment. At the highest software level is the application source code for particular embedded applications. This code is independent of an ECOS but make use of application programming interface to sit on top of an ECOS. This is the GNUM makes a utility of an application source. The GNU cross compiler execute on a source platform that generates a binary executable code for the targeted embedded platform. The GNU links the application object with a code generated by the ECOS configuration tool. The result can be loaded into a targeted system. This is an ECOD layer structures. Here we are focusing on a hardware abstraction layer. Hardware abstraction layer is the software that presents a consistent API to an upper layer and maps the upper layer operation into a specific hardware platforms. Thus, the HAL is different for an different hardware platforms. The demonstration how the HAL abstract hardware specified implementation for the same API fall into two different platforms. These are the two platforms for an implementations. Next, these are the HAL modules. Architecture, variant, platforms. What is architectures? Defines the processor family type. This module contains the code necessary for processor startup, interrupt delivery, context switching, and other functionalities specific to the instruction set architecture for the processor family. Next, variant. The variant supports the feature of a specific processor in the family. Example, the memory management unit. Third one is then a platforms, which supports the tightly coupled peripheral. HAL2 tightly coupled peripheral like an interrupt controller and a time devices. The module defines the platform or a board that includes the selected processor architecture and variant. It includes code for a startup, chip selection configuration, interrupt controller, and a timer device. This is a ECOS kernel design. The ECOS kernel was designed to satisfy the four main objectives. They are low interrupt latency, low task switching latency, small memory footprint, deterministic behavior. Now, in each I will describe. Low interrupt latency. The time it takes to respond to an interrupt and begin executing an ISR is the low interrupt latency. Low task switching latency. A time it takes from when a thread becomes available to when actual execution begins is the low task switching latency. What is a small memory footprint? Memory resources for both program and data are kept to minimum by allowing all components to configure memory as needed. It's a small memory footprints. Deterministic behavior. Throughput all aspect of execution, the kernel performance must be predictable and bounded to meet a real-time application requirement is the deterministic behavior. ECOS kernel also provides some of the core functionality which is needed for developing multi-thread applications. They are ability to create a new thread in a system either during a startup or when a system is already running. Control over various threads in a system, for example, the manipulations, there are priorities. A choice of schedulers determines which thread would currently be running, and the range of synchronization primitives allows thread to interact with an shared data safely. And finally, the integrations with a system support for an interrupt that executions. These three features are not present in an ECOS kernels. They are memory allocations, device driver. This makes for an lean kernel. Now we begin with an ECOS I/O system, which is an input-output system. The ECOS input-output system is the framework for supporting a device driver. A variety of drivers for a variety of platforms are provided in ECOS configuration package. These include drivers for a serial devices, Ethernet, flash memory, interface, and various I/O interconnects such as PCI, which stands for Peripheral Component Interconnect, and a USB, Universal Serial Bus. In addition, user can develop their own device driver. The principal objective of an I/O system is efficiency with no unnecessary software layering or the extraneous functions. Device driver provides the necessary function for an input, output, buffering, and a device controller. These are the three-level interrupt routines. They are interrupt service routine, deferred service routine, and a thread. Now each I will explain in detail. What is an interrupt service routine? It invokes in a response to an hardware interrupt. The HAL, which stands for Hardware Abstraction Layer, decodes the hardware resources of an interrupt and calls the ISR of the attached interrupt object. This ISR may manipulate the hardware but is only allowed to make a restricted set of calls on a driver API. Now, what is deferred service routine? Deferred service routine invoked in response to a request by an ISR. Most of the time, the DSR will run immediately after the ISR. Next one is thread. The client of the driver threads are able to make all API calls and in a particular are allowed to wait on a mutex and a condition variable. Cost scheduler. This is a very important concept. There are two types of scheduling. One is an bitmap scheduling, another is called as a multi-level queue scheduling. In bitmap scheduling, efficient for a small number of thread actives, and each thread has a different priority. In multi-level queue scheduling, appropriate when a number of thread is dynamic and multiple thread and each priority. And third one is time slicing. This is an picture which depicts the bitmap scheduling priority levels. Here, a bitmap scheduling supports an multiple priority levels, but only one thread can exist at each priority at a given time. The scheduler decides, and quite simple with a scheduler. When a blocked thread is ready to run, it may preempt a thread of a lower priority. When a running thread suspends, the ready thread with a highest priority is dispatched. This is a multi-level queue scheduling priority. Here, the multi-level queue scheduling supports up to 32 priority levels. The multiple queue schedule allows a multiple active thread at each priority level. When a blocked thread becomes ready to run, it may preempt a thread of lowest priority. The multi-level queue scheduler can be configured for a time slicing. Thus, if thread is running and there is one or more ready thread at same priority level, the scheduler will suspend the running thread after one time slice and choose the next thread in a queue at that priority level. This is the round robin policy within one priority level. Not all applications require the time slicing. This is an ECOS thread synchronization, which include classic mechanisms, synchronization slash communication mechanisms, and SAP support. And in classic mechanisms, we are dealing with a mutex, semaphore, and condition variables. Next, what is mutex? Which allows only one thread at a time to gain access. The mutex has only two states, locked and unlocked. This is similar to a binary semaphore. When a mutex is locked by a one thread, any other thread attempts to lock the mutex is blocked when the mutex is unlocked. Then one of the threads blocked on this mutex is unblocked and allowed to lock the mutex and gains the access to resources. Next one is mutex differ from binary semaphore in two aspects. First, the thread that locks the mutex must be the one to unlock it. The other difference is that a mutex provides a protection against priority inversions whereas semaphore does not. Next, what is semaphore? The ECOS kernel provides support for counting semaphore. Counting semaphore is an integer value used for an signaling amount thread. If a new count is less than or equal to 0, then the thread is waiting on the semaphore and is awakened. If the count is 0, the thread calling these functions will wait for a semaphore if the count is non-zero. The count is decremented and the thread continues. Another use of semaphore is the resource management. Next, what is condition variables? Condition variable is used to block a thread until a particular condition is true. Condition variables are used with an mutexes to allow a multiple thread to access the shared data. Now, what is an event flag? An event flag is a 32-bit word used as a synchronization mechanism. Application code may associate a different event with each bit in a flag. A thread can wait for either a single event or a combination of events by checking one or more multiple bits in the corresponding flag. What is mailboxes? Mailbox is also called as a message boxes. ECOS synchronization mechanisms provides a means for two threads to exchange information. ECOS mailbox mechanisms can be configured for blocking or the non-blocking on both the send and the receiver side. The maximum size of a message queue associated with a given mailbox can be configured. Next one is the SMP support, which is an asymmetric multiprocessor which includes the spin lock. A spin lock is a flag that is thread can check before executing a particular piece of code. Only one thread at a time can acquire a spin lock. Any other thread attempt to acquire the same lock will keep trying spinning until it can acquire the lock. If the value is 0, the thread sets the value to 1 and enters its critical section. If the value is non-zero, the thread continually checks the value until it is 0. A spin lock should not be used in a single processor system. Next, the another type of operating system is called as a tiny operating system. Tiny operating system is a 400 byte of code. It is not a real-time operating system and it doesn't include kernel. There is no processors. OS doesn't have a memory allocation system. Interrupt and exception handling is dependent on a peripheral and it is a non-blocking. So there are few explicit synchronization primitives. And this is the wireless sensor network topologies. And here we are using internet, host PC, and base stations. These are some of the sensors. TinyOS was developed primarily for use with networks. It is an low cost, small size, low power consumption wireless sensors can be used in the host applications. This is used in the host applications. Here, a base stations connect to an sensor networks to the host PC. This base station is connected to a sensor network as the host PC and passes on a sensor data from the network to a host PC, which can do the data analysis and or transmits the data over the corporate network or an internet to an analysis server. Individual sensor collects data and transmit these to a base station either directly or through the sensors that act as the data relay. These all are the goals of an tiny operating system. They are allow high accuracy, high concurrency, operate with limited resources, adapt to hardware evaluations, support a wide range of applications, supports a diverse set of platforms, and be robust. What is, what is high accuracy? In a wireless sensor network application, the devices are concurrency intensive. Several different flows of a data must be kept moving simultaneously. Sensor data is input in the steady stream. Processed result must be transmitted in the steady stream. External control from remote sensor or a base station must be managed. Next one is operate with an unlimited resources. TinyOS will have limited memory and computational resources and run on batteries or solar power. A single platform may offer only kilobytes for a program memory and hundreds of bytes of RAM. Adapt to hardware evaluations. Application and most system service must be portable across hardware generations and thus it should be possible to upgrade the hardware with a little or no software exchange. Next, support a wide range of applications. The wide range of applications exhibits a wide range of requirement in terms of lifetime communication, sensing, and so on. Support a diverse set of platforms. As within a preceding point, a general purpose embedded application is desirable. Be robust. Once deployed, sensor network must run unattempted for the month or a year. This is an timer M components. Now, before dealing with this, I will tell you TinyOS component. An embedded software system built using TinyOS consists of a set of small modules called component, each of which perform a simple task or a set of tasks and which interface with each other. Components include single hop networking, ad hoc routines, power management, timer, and the non-volatile storage controllers. Here, the shaded box. The shaded box is in a diagram indicates a component which is treated as an object that can only be accessed by the defined interface indicated by an white boxes. A component may be hardware or a software. A software components are implemented in a nested C and which is extension of C. This is an module M timer. Provides an interface standard controller, interface timer, and it uses an interface clock as clock. This is the timer M configurations. A task is a component is similar to a thread in an ordinary operating system with certain limitations within a component task atomic. Once a task has started, it runs to completion. It cannot be preempted by any other task in the same component. There is a no time slicing. A task cannot block or spin a wait. Command. Commands are a non-blocking request, that is, task that issues a command does not block or spin wait for a reply from a lowest level component. A command is typically a request for a lower level component to perform some services such as initiating a sensor reading. This is a configuration timer and this is then an implementation timer. Next one is TinyOS schedulers. The TinyOS scheduler includes operates across all components, only one task executed at one time, and simple FIFO queuing operations. Scheduler is a power aware, puts a processor to sleep when no task in a queue. This is an search example of an tiny operating system, and this search describes the performance periodic sensor sampling and uses ad hoc multi-hop routines over the wireless network to deliver samples to the base station. This is the configurations for an search. This is an main. This is an standard controller. Main is an component. The search is an search component. Photo, timer, C, and multi-hop are the components. TinyOS resource interface. TinyOS provides a simple but powerful set of conventions for dealing with resources. They are dedicated, virtualized, shared. In dedicated, resources that a subsystem needs exclusive access to at all times. In this class of resource, no sharing policy is needed, since only a single component ever requires use for these resources. In virtualized, every client of a virtualized resources interact with it is if were dedicated resources, with all virtualized instance being multiplexed on top of a single underlying resources. The virtualized abstractions may be used when underlying resources need not be protected by mutual exclusions. An example is a clock or a timer. In shared, what happens? The shared resource abstraction provides access to a dedicated resource through an arbitrary component. The arbiter enforces mutual exclusions, allowing only one user at a time to have access to a resources and enable the client to block the resources. And the shared resources configurations provides following interfaces. They are resource requesters, resource configurations, and the resource specific interface. This is the shared resource configuration example. Thank you. Thank you, sir.